Welcome back. So today we are going to be looking at, or starting our chapter on electrochemical cells, focusing on voltaic cells first. Then we're going to be looking at how to get the cell potential or the voltage of a cell, and then move on to something called electrolytic cells. So what we have right here on the first page, you guys will notice, is a bunch of different definitions. So I'm just going to point out a few kind of important ones, then kind of refer back to this page as we kind of go through. And of course, the first one is we're just going to be looking at, definition of an electric cell. That is just something that continuously converts chemical energy into electrical energy. So that is why we are kind of doing this, where electrochemistry, we're focusing on this. Now for our voltaic cell, this is what we're going to be focusing today on. It's a cell that spontaneously produces electricity. So it uses a spontaneous reaction in order to do this. Now also we're just going to look at three other ones right here. So this is going to show up a lot, the term electrode. So this is a solid electrical conductor. You'll notice solid is highlighted here or in bold. That is because whenever we're drawing cells or trying to figure out what's in an electrochemical cell, we need to have an electrode, and it needs to be something that's solid. And then, of course, our anode and cathode. An anode is a negative electrode. Cathode is our positive electrode, or sometimes it's referred to as negative terminal and positive terminal. So if you think back to if you've ever seen a battery, how it has the positive and negative end, this is what they're talking about here. So the anode is always the negative, cathode is the positive. Then, of course, finally, last thing, just kind of bring into light as well. Just remember electrolyte. So we covered these in Chem 20, and these are just aqueous electrical conductors. So they contain cations, which are positively charged, and anions, which are negatively charged. All right, now, one of the things that we're going to see as well, because we are going to be dealing with electricity and a lot of this stuff as well, we are going to have to deal with some of these new things. Now, if you've done physics, some of the stuff, so charge, current, potential difference, you've seen this before. If you haven't, that's fine. We're just going to have a quick little, what's the symbol, what's the unit, and what does the unit symbol look like. So charge, the symbol for that is Q. Now there is no meter to measure charge, so you can't really hook anything up to measure what the charge is. However, the unit that we use to measure charge is a coulomb, and the unit symbol for coulomb is C. Now current, the symbol for that is I. Now this one is going to show up, and same thing with potential difference. So these here are going to be the important ones. Now we measure current with something called an ammeter, and the unit we use to measure is called an ampere. So an ampere, the unit symbol is A, or the base definition is a coulomb per second. So what that means is how many charged particles go past a certain area every second. Now the potential difference, the symbol for that is V. We measure this with a voltmeter. Now voltmeter in a diagram will look like this, and just go back up, ammeter will look like this. Just kind of V or A in a little circle. Now potential difference, the unit for this one is volt, and a volt is represented by V. And the definition of a volt is joule per coulomb. Now power, you may come across this. So power, the symbol for that is P. There's no real meter to measure that. We do have a unit for it is a watt, and a watt is how many joules per second something uses. So that's where if you do measure the power usage for something is in watts, and watts just how many joules, so how, the potential, how many joules is used every second. And then of course energy density, it should be a C, not a D. The symbol for this, there is nothing. This normally shows up when we talk about certain materials, like if you have a kilogram of uranium, how much energy can you get from that? So you kind of measure energy density. And of course the unit for that is joules per kilogram, which is just joules per kg. So we'll kind of get into some of these here, especially current and potential difference is going to show up a fair bit throughout this unit. Now, like I said, we're focusing today on voltaic cells. So what are voltaic cells? And we will be defining a bunch of different things. So anode, cathode, anion, cation, salt bridge, all those little things up there. So, as a redox reaction involves a transfer of electrons from a reducing agent to an oxidizing agent. So this is nothing new. We know that in electrochemical reactions, we have a transfer of an electrons. Well, what a voltaic cell is, it uses spontaneous chemical reactions to generate electricity. So they managed to do this by the transfer of electrons occur through an external wire rather than directly from the strongest reducing agent to the strongest oxidizing agent. Because when we mix two solutions together, chemical reagents are able to collide together and transfer the electrons as they collide. Now what we're going to do is actually physically separate our oxidizing agent and our reducing agent and connect them using a wire. So this is a wire here. Now what's able to happen when we do this, so our strongest reducing agent we know is oxidized, and oxidation is a loss of electrons. So our electrons are able to leave, go through this wire, and go to our strongest oxidizing agent, which is reduced. And it's all connected by a wire. Now we can measure the potential difference, we can measure the current, anything like that, but the main thing is that we have our strongest reducing agent is still being oxidized, the electrons are still going over to the strongest oxidizing agent and still being reduced. Now one thing we'll have right here, so anode, this is going to be, so this represents that solid electrode. So the anode, this is where the action or the reaction actually occurs, and oxidation always happens at the anode and reduction always happens at the cathode. So you know the anode is our negative terminal, so this will always be the case. For every electrochemical cell. So that is how they are defined. So not only now do we have processes of strongest reducing agent and of course oxidation, now we can also refer to them as the anode as well. So we have technically three terms to kind of describe what is happening on a particular half reaction or a half cell reaction. All right, so just remember it's the anode is the negative electrode, and it must be a solid. And of course this is where the loss of electrons is happening, so that's why we had LEO. So for that acronym, Leo to Lion says GER, so loss of electrons is oxidation. Our strongest reducing agents occur here. Now common strongest reducing agents, we're going to see metal elements or non-metal ions generally happen. Now for these here, the mass of the anode normally decreases. Now it's not going to be every single case, it just depends on what is reacting, but the reason it's going to decrease because if you have a metal solid and is being oxidized, that means it's producing a metal ion and an electron. So because we're starting with a metal solid, and now in order for this reaction to occur, the mass is that the metal solid is actually being reduced because it's forming into the ion. That's why the mass generally decreases. Now also these are going to be connected by electrolytes, and we always have the anions are going to move towards the anode. Now just kind of put that in the back of your minds, because when we start drawing diagrams and explain what's going to happen, they'll make a little more sense. Now for the cathode portion, this is the positive electrode. Remember, it is solid. And of course here, the gain of electrons is reduction. Strongest oxidizing agents occur here, and our common oxidizing agents is non-metal elements and metal ions. Now, at the cathode, the mass is generally going to increase, because if we're talking about metals, and like if we do look at our data booklet, when you look at a lot of the things that go on here, there's a lot of metals, right? But if you notice a lot of the reduction half reactions, we have stuff like, I just make this a little bigger. We have stuff like copper turning into copper solid. We have lead turning into lead solid, tin turning into tin solid. So we see a lot of ions turning into solids on this half reaction here. So that's why the mass normally increases if we're starting with a metal ion, and then we have getting an electron turning into a solid. And of course, the movement of the ions, we're going to get cations move towards the cathode. Now the cathode is labeled positive since the anode is labeled negative, and the reason the anode is labeled negative is that's the source of the electrons, right? Because electrons are negatively charged, so they're going to come from the negative end. So technically what's happening at the anode is the electrons are being pulled away due to their lower electronegativity. So this still kind of goes back to the whole thing. The driving force behind this is the electronegativity of the reacting species. So electrons always move from anode to cathode. Now, speaking of the voltage and the current. So the voltage depends on the materials used or the type of chemicals involved. So our next lesson, the one that's going to be right after this one, is we look at the potential difference, so how to calculate the voltage. Basically, it only depends on what is used, right? If you have tin and iron, that's going to create a certain voltage, and it's always going to create a certain voltage. Whereas the current, it depends on the size or the amount of material, because there are just more electrons available. The more you have, the more electrons, so you're going to get a higher current. So this is going to become apparent when we do our cell stoichiometry, because we are going to see the current is affected by how much is there. Alright, so just like when we started with redox reactions, we are looking at cell reactions. So to study what occurs in an electrochemical cell, the cell is going to be split into two parts. Right, so we had half reactions to analyze redox reactions. Now we're going to have half cells to analyze an entire cell. Now for a half cell, what is going to be a little different with these here, we need an electrode, so remember the solid portion, but we also need an electrolyte, which is an aqueous thing. Just remember, electrolytes help electricity move, so that's why we need to have that solid electrode, and the reason that's there, so it's something connect to the wire, and of course something to help the electrons and everything move. So half cells, an electrode, and electrolyte combination, forming one half of a complete cell. So this makes it easier to study the parts of the cell, just like when we studied half reactions. So each half cell consists of electrode and electrolyte, and they need to be separated by a porous boundary. So this is because if we have our oxidizing agent and reducing agent touching, they're not going to generate electricity because they're just going to react when they come in contact with each other. So we need to physically separate them. So that's why we have a porous boundary, and that's going to separate the electrolytes and allow ions to slowly pass through to maintain electrical equilibrium. So that's why we're not going to build up a charge on any side of our half cell. Now the two types of porous boundaries that we're going to separate stuff by is something called a salt bridge, and the other one is a porous cup. So from our diagrams right here, we can tell what a salt bridge looks like. Now we can tell that these two half cells are completely separated and are only connected by this salt bridge right here. Now what this salt bridge will allow, all it is just a glass U-tube filled with a non-reactive electrolyte. So what happens is that once this reaction goes, so as the electrons leave one side and go to the other, we can get our ions flowing as well. So if electrons are leaving right here, this is the anode because oxidation is happening on this side. So we're going to get our anions, so our negative ions are going to flow into the solution here to help maintain that electrical equilibrium or electrical neutrality. And same thing right here, if we're gaining electrons over on this side, this would be our cathode. So we're going to get positive ions, or our cations, moving over to this side, because basically if we're gaining one electron over here, we're going to need one positive ion over here as well to cancel out. So we're not going to build up a charge. Now that's how the salt bridge works. Now how the porous cup works is that we have the exact same thing, except now we see we have a cup within a cup here, but this cup allows for the ions to flow through. So as the electrons leave and go from one place to another, we can also get the ions flowing through solution here to help maintain equilibrium or electrical neutrality. Now sometimes we will need an inert electrode tossed in here. So this is a solid conductor, once again solid because it's an electrode. It will not react or interfere with the reaction of the cell. So generally this is used to conduct electrons when the oxidizing agent does not have a metal form or there's no solid in the half reaction. So the common one we use, carbon or platinum. I like to use carbon a lot just because, well, it's cheap and it just doesn't react. So for examples, when you need to use an inert electrode, if you have something like Fe2 plus going to Fe3 plus an electron, right? So this is one oxidation half reaction, but you notice that there is no iron solid in this half reaction. So if this was going to be the reaction at our anode, we're going to need to use an inert electrode. Now I know what you're thinking, why can't we use solid iron? Well, the problem with that, and this is why we use our inert electrodes, is that if we have something like solid iron, which is right here in our data booklets, now as we produce iron 3 right here, we'll notice this is a spontaneous reaction. So as soon as we start producing a little bit of, or as soon as that iron 3 is in solution, boom, it reacts with the iron. We no longer have an electrochemical cell, we just have a spontaneous reaction between iron 3 and iron solid. So that's why we just can't use it. And another one, or another example as well, let's just say if we're dealing with the cathode half reaction cell reduction, and we want to have a really strong oxidizing agent. I know that was a reducing agent there. But for example, let's just say we want to use a very strong oxidizing agent, like if we wanted to get our acidified dichromate. So this reaction right here. Well, notice that in this reaction, so we have aqueous, aqueous, electrons, aqueous, liquid. There's no solid in this half reaction either, and we know this is a very strong oxidizing agent. So it is very possible that we would want to use this for an electrochemical cell because this is a strong oxidizing agent, but there's no solid in there. So this is another example where if we have just hold on a sec. So even this example right here, there is no metal or no solid being consumed or produced. Therefore, we will need to use what we call an inert electrode if we want to use this as my reducing agent, or if this is my oxidizing agent, we would need to use these inert electrodes if these were part of our half cell. Now, last but not least, before we get into actually drawing them, we're going to look at cell notation. So cell notation is just a way that instead of like actually drawing them out, because you can imagine that where we had these diagrams right here, drawing these out every single time can be a bit of a pain because you're just kind of drawing it if you don't have a lot of space. So cell notation is just a way that we can actually communicate what is happening within a cell without actually taking up all that space to draw. So how cell notation works, we always start with our anode to the furthest left, so that's our solid. Then we have our aqueous solution or our electrolyte. Now we'll notice that this little single line right here, so this is a phase boundary, so that is the interface of solution and electrode. That's it. Whereas we get that double right here, this indicates the physical boundary. So this can either be our porous or salt bridge. Then we have our other electrolyte solution, and of course our cathode is our solid. So that is kind of how this will always look. Now, it may be switched up on you, so you should always kind of look for the strongest oxidizing agent, reducing agent, which we'll kind of get into later. Now, also you might see commas in there, so this just is going to separate entities in the same phase. So if there's multiple things in solution there, you're going to see commas just separating them. All right. Now, for an example, just going to show you on how we can actually pick out something if we have a cell notation, how we can pick out our half cell reactions and redox reactions and all that fun stuff. So in the examples going from cell notation, if we have something that looks like this, zinc solid, so that's my solid anode. My electrolyte solution is going to be zinc 2 plus, and we're going to get NO3 minus. So these are the aqueous, so you'll notice how that comma goes in here. We have next but not least, oh, sorry, that just kind of froze up on me for a second. Then we have our phase boundary, then our next electrolyte solution. And then all right. So this is kind of everything that we have right here. Now normally how this will go are anode, electrolytes, and cathode. Now to figure out what the reactions are actually going to have, this is when we can actually split them up. Because of the phase boundary, they're actually physically separated. So in order to figure out what is going to react, of course, is are going to half cell reactions between our SOA and our SRA. So in order to get that, well, we just go to our data booklet. And we just figure out zinc 2 plus, copper 2 plus, and copper solid where they actually fit. Now we know this is going to be a spontaneous reaction, so we have to make sure they follow the spontaneity rule. Now when we actually go through, we see our zinc 2 plus and zinc solids right here, and we see our copper 2 plus and our copper solid. So we know copper 2 plus is my SOA, my zinc solid is my SRA, and of course this is a spontaneous reaction. So we know that the copper solid isn't reacting and the zinc 2 plus isn't reacting, but that's fine. So now that we know that, my strongest oxidizing agent, got Cu2 plus. Oh, sorry. Oh, yes, that was right. I have that one, my strongest reducing agent. And to put them together, cell or our redox reaction is just going to be Cu2 plus zinc solid producing Cu solid plus zinc 2 plus, because the electrons cancel out. So that's how we can go from, as long as we have our correct orientation here and we still kind of follow the rules of figuring out what our strongest oxidizing agent is, our strongest reducing agent, we can figure out what should be a reaction. And of course we know this is spontaneous. Now, before we get into actually drawing them, stuff like that, just something else that you should see. So a standard half cell, if you see this word pop up at any time. So what a standard half cell is by definition, it's a half cell that has everything that is in its half reaction of your data booklet. So for example, a standard nickel half cell. So when we look at our data booklet with nickel, right, so we'll just clear this off. When we find nickel, is right here, right? Everything in there now, we can't put in electrons that's going to be generated. We have our nickel 2 plus ion and nickel solid. So our standard nickel half cell is going to have nickel solid and nickel 2 plus ion present. Whereas if we have the standard chlorine half cell, it's going to have both Cl2 gas and Cl minus present, right? So when we're trying to figure out what needs to be present for our standard hydrogen half cell, what should it contain? Well, same thing, we go to our data booklet, we find the reaction of hydrogen, and where is it? It's right here. So our standard hydrogen half cell is going to find a way to contain hydrogen gas, but also have the hydrogen ion. So it's going to have the hydrogen ion, just aqueous, and hydrogen gas present. So two of these together will need to have, well, what will make a standard half cell. And we'll notice standard half cell, aqueous gas, there's no solid, so this will need an inert electrode. Right, so going back to that thing about inert electrodes, if there's no solid showing up inside of that half reaction, you'll need to have an inert electrode there. All right, so this is common practice to write cell notation with the anode on the left-hand side and the cathode on the right-hand side. But just remember that's not always going to be the case, so always try to find your strongest oxidizing agent and reducing agent and figure out which one's losing the electrons, which one's gaining the electrons before you can draw it out. Now when we're drawing cells, and this is just going to be our last thing, so going from cell notation to actually drawing them, this is how it generally looks. So a typical voltaic cell will look like this, where we have two beakers. We have these things right here, so beakers. We have our electrolyte. We have our electrode. We have our wire, salt bridge, and so on. So this is typically how they're going to look. Now, where you can draw a porous cup as well. When we get into some of these diagrams, we'll end up drawing both. Now, normally anodes on the left, cathodes on the right, but you can draw it whichever way. As long as you have the flow of the electrons going the right way, you should be fine. Let's look at our first example, where it says draw and fully label the following electrochemical cell, including half cells, reactions, and the net reaction. So there's a lot of stuff going on right here. Now the reason also I kind of have this example, we will notice carbon is showing up here. So we know carbon is our inert. Our inert electrode. And the reason for that is when we look at the combination, we can see the hydrogen half cell here, H2 gas and H plus aqueous. We can tell that this is one half cell here, right? And obviously the chloride ion, that's just one of the ions that show up. It probably won't react, but anyway, we'll see. So first, when we get going, we can either draw the cell first or we can put in all the reactions. I'm just going to draw the cell first. So normally when we draw, we can draw whichever way we want. So we start by drawing our two beakers. Then if we want to, we know that there's going to be our solid electrodes going to show up. These are connected by a wire. We can have a voltmeter attached, and there's going to be solutions involved. And we have our salt bridge. So this is just a very, once again, quick, easy way of drawing it. Now it's just a matter of kind of putting everything in. Now I'm just going to draw everything from the diagram that's up here. So the fact that we have our solid, and this is the anode portion, so we know this right here is zinc solid. And our electrolyte solution is zinc 2 plus and NO3 minus. So that's one half of our cell over here. Our other half, after a phase boundary, our electrolyte solution is H plus and Cl minus. Our solid is carbon solid. Now also what needs to be attached to here as well, and it's going to be hard to draw, but you can just kind of have gas molecules around, and this is our H2 gas. Right, so there needs to be a way to obviously contain this, so you could have a dome over this little side, but there should be hydrogen gas kind of around this area. Right, we're just going to draw that by dots. All right, so now that we have that, we can start putting, now before I label everything anode and cathode as well, I do need to go off and figure out what is my strongest oxidizing agent, strongest reducing agent, because I can't assume that this is my anode and cathode. So let's look at our data booklet. Now, same thing, like these are basically all of our entities listed that was right there, so we need to find strongest oxidizing agents and reducing agents. So we know we have zinc 2 plus and zinc solid, so that was there, but we also had hydrogen plus and H2 gas. So hydrogen plus is strongest oxidizing agent, zinc solid is strongest reducing agent. So we know strongest oxidizing agent, this is my cathode portion, strongest reducing agent, anode. Perfect. And that's exactly how I have it drawn there. So now that I know this, I can call this my anode, and it's negatively charged. Carbon solid is my cathode, and it's positively charged. And the electrons are going to leave from my anode to my cathode, and I know my anions, negatively charged ions, are going to go here from the salt bridge and my cations go here. So that is kind of fully labeling our cell. We have everything that we have, or everything that we need. Now from here as well, now we can, so that is our electrochemical cell, done. Include the half reactions and net cell reaction. So because I've already figured out this was my strongest reducing agent, this was my strongest oxidizing agent, I can do my reactions. My strongest reducing agent, zinc solid, turning into zinc 2+, plus 2 electrons, and my strongest oxidizing agent was 2H+, plus 2 electrons, producing H2 gas. And when we add these together, the electrons cancel out, and we are left with this cell reaction. So zinc and hydrogen react to produce the zinc ion and hydrogen gas. So that is how we go about fully labeling a cell, and of course figuring out the half reactions and the redox. Now our next one says draw and fully label a voltaic cell consisting of a carbon and copper electrode, copper 2 nitrate solution, and acidic potassium dichromate solution. Include half cell reactions and net reactions. Just remember, this is an inert. This is an inert electrode and is only used for a half reaction that has no solid. Now, just to give you a hint, a copper electrode pairing it with copper 2 nitrate, we need to pair those up. Just because we have our solid copper and copper 2. We know 2 of these can go together because if we check our data booklet, we see copper 2. If I can find copper 2, here we go. Copper 2 and copper solid pair up nicely, right? And then with the other one, dichromate, when we look at this entire half reaction involving dichromate, I think it was dichromate. Yeah, acidic potassium dichromate solution, absolutely. When we look at this right here, we have acid, we have dichromate, we have chromium, we have water, but there is no solid, so our carbon needs to go there. All right, so I'm just going to let you try to draw this one on your own, and then in 3 seconds the answer will show up. All right, so just give this one a go on your own. Great, and when you're done you should get something that looks like this. Now I decided to use the porous cup diagram this time, but you can use whichever one. So we still have our anode over here, cathode over here. So our strongest reducing agent in this case right here out of everything was our copper solid. So that's what we have right here at the anode. And then of course the solution was the copper 2 ions. And I could have put in, it was nitrate, so I should have put in nitrate as well. So we also have NO3 minus, a little jumbled inside that little cup, but that's fine. Then the other side, our cathode, we have our acidified potassium dichromate solution right here. Because there's no solid in that half reaction, we have our carbon solid acting as our solid electrode, or our cathode, which is positively charged. And of course, the electrons go from anode to cathode as drawn right here, and our anions go towards our anode, our cations go towards our cathode. And as for the half reactions, have it exactly how we've written it right here. So our strongest reducing agent should react like this. Our strongest oxidizing agent will react like this. So these are just pulled directly from our data booklets. And of course, just like you've been working on all along, when we add 2 half reactions together, we have to make sure that the electrons equal out. And that is to multiply the top one here by 3, and we get our cell reaction. Now on the last page right here, and that is it for the cells, is just kind of, once again, some old diploma questions right here, where we're looking at something like this and trying to figure out what is going to be an oxidizing agent, what is a reducing agent, and all this fun stuff. Now, of course, when we have an electrochemical cell, when it's drawn out, we do not assume that the anode and cathode's over here. Our first step is we're going to go to our data booklet, just like this, so we know we have copper solid, copper 2+, nickel solid, nickel 2+, and figure out what is our strongest oxidizing agents and what is our strongest reducing agents. And this is all I'm going to help you with, and ask you guys to solve this on your own. So we have nickel 2 plus and nickel solid right here. You got copper 2 plus and copper solid over or up here. Sorry, my screen just froze, I think. Oh, here we go. And we got copper 2 plus and copper solid here. So obviously the copper 2 plus, strongest oxidizing agent, nickel solid, strongest reducing agent. So when we go back, we had nickel solid, strongest reducing agent, and strongest reducing agent is oxidized, so that makes this side my anode. And we have over here, this was my strongest oxidizing agent, which makes this my cathode. And the electrons flow from the anode to the cathode. And that is the main thing getting set up when you're given the diagram like this. Do not assume that it's set up properly. Assume that someone might have made a mistake while drawing it, and then try to figure out what side's your anode, what side's your cathode. And then from here, you should be able to answer these questions. Like, for example, I'll let you guys kind of answer this right here, and then I'll have the answers up in a few seconds. And the answers look like this. So for D, this one in the cell above, the reducing agent, of course I already had this one listed up there above, was the nickel solid. And the oxidation number, of course, is going to increase. So when in doubt, I drew the half reaction right here. So we had nickel solid element, oxidation number is 0, going to positive 2, that is an increase, right? So make sure to doodle all these here. Try not to answer this in your head. You're just going to end up hurting yourself or getting confused, right? So make sure to draw it down. Same thing with 19, during the operation of cells, species being reduced is, of course, copper 2 plus, because that was my strongest oxidizing agent. And the mass of the copper electrode, well, same thing. I draw out the half reaction that's happening. We have copper 2 plus, it's gaining electrons and producing copper solid. So we're having an increase in copper solid, so that is the mass increasing. All right, so that is it for voltaic cells. Next lesson, we're going to look at electric potential, so calculating the voltage of these cells, and then we're going to be looking at the other end, the non-spontaneous ones. So please go to your workbooks, try to practice as much of these as possible, and if you have any questions, make sure to email me right away. But anyway, that is it for this one. I'll see you guys for the next lesson.